This is the screencast for section 3.4, example 6. We're going to study sensitivity to change. So change gives you a little foreshadowing that we are going to be dealing with derivatives. The Austrian monk Gregor Johann Mendel, which you may have heard of him before, working with garden peas and other plants, provided the first scientific explanation of hybridization. His careful records show that if P, a number between 0 and 1, is the relative frequency of the gene for smooth skin peas, so I assign that 0.25, so in other words 25 out of 100 are smooth skin peas, and that's our dominant gene. And then 1 minus P, the relative frequency for wrinkled skin peas, so that would be 0.75 then, or 75%, 75 out of 100 would be wrinkled. Now those recessive. Then the proportion of the smooth skin peas in the next generation will be determined according to this formula, says Mendel. So I plugged in my 0.25 and my technically 0.75. And as you may have predicted, the dominant gene becomes stronger in the next generation, going from 0.25 to 0.375. Now this piece was not necessary, but sometimes once you understand what's happening numerically in the problem, it's a little bit easier to make sense of what's happening in its derivative. So let's do that. Let's compare the graphs of y, which is up here, and dy dp. Well, we've got to find that. So dy dp equals, let's see, y was 2p minus p squared. That would make the derivative 2 minus 2p, which is graphed over here, dy dp. The line whose slope is -2 and y-intercept is +2. You can see up here my scale does go from like -0.2 to +2.2, but I've scaled it 2.1 on the y-axis, so that's why you see so many marks. Anyway, we want to determine what y values are more sensitive to change in P. So what y values are more sensitive to change. Sensitive to change would mean they change faster, which means you're looking for the highest values of dy dp. Alright, so I'm going to look at my graph of my derivative. Here on the x-axis are my p values, and then on the y-axis are my dy dp values. The highest rate of change, the fastest rate of change, results in p values closest to 0. But it's not asking me about p values, it's asking me about y values. So I need to go back to my graph of y, and those p values that are really close to 0 also produce y values really close to 0. So my concluding sentence can say something like, y is more sensitive to a change in p for p values closer to 0, which results in y values closer to 0, according to y of p, which would be this graph up here. This graph up here is the function y, whose input is p. This one is the derivative of y with respect to its input, p. The now try problem, number 25, talks about draining a tank. It takes 12 hours to drain a storage tank by opening the valve at the bottom. The depth y of the fluid in the tank, t hours after the valve is opened, is given by this formula. So y is depth and t is hours. Part A asks us to find the rate, dy dt, which would be meters over hours. They give us meters here too in the formula, at which the water level is changing at time t. So let's find dy dt. Well, to take the derivative of this function, I kind of have a composition function here. I've got a function in parentheses inside of a squared. So I can't really use the power rule, because if I just take the 2 and make it a coefficient, I'm changing the essence of the inside of this problem. A square around these parentheses means y is really 6 times 1 minus t over 12 times 1 minus t over 12 again. So if I multiply all that out first, then I can just use the power rule. So now that I've got y as a function of t, I can use the power rule because I have a basic variable t to an exponent with a coefficient. So dy dt is going to be, let's see, 2 times 1/24 is 1/12, t now to the positive 1 power, done with that, minus, and then the derivative of t is 1, plus the derivative of 6, but the derivative of 6 is 0. So this expression right here gives us what the question asked. It is a rate at which the water level is changing at time t. So no matter what the time is, I could plug that in and find out what rate the water is changing. I don't know if any of you have ever washed dishes before, but I just got done washing dishes. If you fill up your sink and then wash your dishes and then you pull the drain out, it seems like it takes forever for the water to drain at first, but then at the end, as the bowl gets smaller on the bottom, as your sink gets smaller, it seems like the water just rushes out of there. That's because the water is draining at different rates. And that's what this study is doing here. Part B. When is the fluid level in the tank falling fastest, slowest, and what are the values of dy dt at these times? So over here to the right, I've graphed dy dt, which is a line whose y-intercept is -1 and has a slope of 1/12. The fluid is falling the fastest here at time t equals 0. I know that this is the lowest value on the derivative graph, but remember, velocity is directional, so a negative velocity, this is -1 meters per hour. And here we're going -0.5 meters per hour, 0.3, 0.2, 0.1, and then 0 meters per hour. So we're slowing down as the velocity graph is approaching 0. So again, when is the fluid level in the tank falling the fastest? The fastest is going to occur at t equals 0, and dy dt of 0 is -1 meters per hour. The slowest is going to occur at t equals the x-intercept, which would be 12, and the rate would be dy dt of 12, which is 0 meters per hour. Part C, graph y and dy dt together and discuss the behavior of y in relation to the signs and values of dy dt. This is kind of a confusing set of directions. Discuss the behavior, very vague. So let's look at the signs and values of dy dt. First of all, dy dt is always negative. Oh, this is y, by the way. Dy dt is negative, so we'll say that dy dt is less than 0, and that's due to what behavior of y? Well, because y is decreasing. Now, as far as the values of dy dt, the values of dy dt are increasing and approaching 0. Why would that be happening? Let's see here. If I look at these slopes, that slope is pretty steep. That's going to get a little bit shallower. That's going to get a little bit shallower, and they're shallowing out. Can you think of a characteristic in y that would cause these negative slopes to shallow out? It's because it's concave up. Because y is concave up. Dy dt is negative because y is decreasing. So those slopes are negative. Y is going down. However, those slopes are getting bigger. The slopes are increasing because y is concave up. If y was concave down, those slopes would start out at 0 and go negative and negative and negative and negative, more negative, so they would decrease. That's concave down. Concave up, the derivative values are increasing.